Hey folks, in lesson 23, we're going to be talking about a specific type of collision, which is a collision between a particle and a fixed surface. Now, a lot of the notation, a lot of what we're talking about is going to be very similar to the collision of particles, but don't confuse the two because we can't make the same assumptions. In particular, we can't make an assumption that total linear momentum is conserved in this situation. And so let's walk through those steps and see how that affects how we model this collision. Now, the first thing to point out are the similarities between a collision of a particle on a surface and a collision between two particles. And the first is that we're given the initial velocity of the particle, and we want to determine the velocity after it collides with a fixed object. So this is similar to what we had before, where we were given velocities of two particles, and then we needed to determine the velocities after they collided. The next thing that's very similar is the phases of the collision. So we still have, in this case, an initial phase, and in this initial phase we know the velocity. And then we have our final phase in which we're determining the final velocity. And we have this impulse in the middle. So in this impulsive phase, let's separate these. We have an impulse that's occurring here in the middle, and we have the same times that we were dealing with before, which we're saying that at time 1 is where the collision begins, and it's at time 2 in which the collision ends. And so this is the impulse, and then we have a time in the middle that we call time C, which is the time in which our particle is squished the most. It's our maximum compression. And then we have these pieces, these phases here, where we have a deformation, and then from Tc to T2 we have restitution. So this is exactly the same. We have 4 phases: deformation, restitution, an initial phase, and a final phase. And we're going to model this, you'll see, by looking from T1 to T2 initially, just like what we did last time, and then we're going to break it down into modeling T1 to T2, T1 to Tc during deformation, and then Tc to T2 during restitution. Now, a difference is that notice here that the velocity of P with respect to O doesn't give us the plane of contact like what we had before. But instead we need to define the plane of contact differently. And so our collision frame here is going to be based completely on the orientation of the surface. So let's show that. We need to have a line of impact which we're going to say is perpendicular to the surface. So when we write our collision frame using our same basis vectors in which we have E sub n, E sub t, and then E sub 3, we have an inertial reference frame where we have E sub 1, E sub 2, and then we have an E sub 3 pointing out of the page. And then we define our collision frame as its origin at O prime, which is the point of contact, and then we'd have our E sub n vector, which is perpendicular to the surface. And then E sub t, defined as E sub 3 crossed with E sub n, and when we take the cross product, we get a vector that's along E2. And so we're showing here that instead of the line of impact being defined by the relative velocity, as we did earlier, we're simply defining it by the surface itself. And so now let's deal with the collision dynamics. Our assumptions that we're making about our collision dynamics, once again, are similar, and we see similarities in the first 4, in which the first assumption is that the collision occurs over a short interval of time, and this is very important because it allows us to use our relation of impulse and momentum. our assumption number 2 is that the moving object is a point mass. And so our surface is a surface, and then our mass is a point mass. This is a slight change because we don't have 2 point masses anymore, but one is a surface. Assumption number 3 is the same, is that there are no external forces that are acting on the particle. And I'm sorry, assumption number 3. Assumption number 4 is the same, is that we don't have any friction between, in this case, the particle and the surface instead of 2 particles. And so that allows us to model our interactive force, or our impulse, only along the line of impact. But we do have one new assumption, and that is that the surface is rigid and that it's fixed at the point of contact. And so by being rigid, that means that the surface itself is not going to deform. And this is a big difference because in lesson 22, when we were talking about the collision of 2 particles, both particles deformed and then rebounded. In this case, the surface itself we're assuming is rigid. And then if it's fixed at the point of contact, then what we're saying is that there's no velocity during the contact of the surface. So we'll start our analysis by analyzing the collision from time 1 to time 2. And that is from the beginning of the collision all the way to the end of the collision, so it takes into account the entire impulse. And we'll do that by applying the impulse form of Newton's second law, which is the mass of particle P multiplied times the velocity of P with respect to O, as observed in the inertial reference frame at time 2, is equal to the mass of P multiplied times the velocity of P with respect to O, observed in an inertial reference frame at time 1, plus the impulse from time 1 to time 2. And so to complete this, we need to have a free body diagram of our particle. And so here we see that the force acting on this particle is going to be, using our collision frame, will be our impulse from time 1 to time 2 is equal to the negative impulse, the magnitude, time 1 to time 2, in the en direction. And this is using the collision frame that we defined earlier, where en is pointed to the right. We also need to define our speeds in terms of the collision frame. And so our velocity, P with respect to O, at any time t, is going to be the speed, U sub P, and this is in the tangential direction, plus the speed, V sub P, and this is in the normal direction. And so when we insert our velocities for time 1 and time 2 into our impulse momentum, which is Newton's second law in impulse form, and then we solve for our scalar equations in the tangential direction, in the normal direction, so in the line of impact and the plane of contact, then along E sub t, we get the relationship of our mass of P multiplied times our speed in the tangential direction at time 2 is equal to the mass of P multiplied times the speed in the tangential direction at time 2 is the same as time 1. And then in the E sub n direction, then we get mass of P, V sub P time 2 is equal to the mass of P, V sub P at time 1, minus the magnitude of our impulse from time 1 to time 2. And so with these two relationships, we see two very important things. Okay, we get a similar result from our tangential direction, which says that our speed in the tangential direction at time 2 is equal to our speed in the tangential direction at time 1. And so this result gives us a nice easy solution for the speed in that direction, in that we're going to conserve momentum in the tangential direction. Okay, and we see that when we're given that initial condition, we can simply just move that to time 2 and use that solution. Now, when we look in the E sub n direction, which is along the line of impact, we see something really important that we didn't have when we were colliding two particles together. And that is that momentum is not conserved along the line of impact. Okay. Now, when we had two particles that were colliding together from lesson 22, momentum was conserved along the line of impact. So this is a key difference. Momentum is not conserved along E sub n. And so what this means is that we've got this unknown taken care of, which is our speed in the tangential direction at time 2, but we still need to find the speed in the normal direction at time 2. So we've still got this one unknown left over, so we now need to do some more work to determine what that speed in the normal direction at time 2 is. And as you might guess, we're going to use the coefficient of restitution to determine this. So to go there, we need to look at our impulse now and divide this into two parts, where we're now looking at time 1 to time c, so this is during the compression or deformation, and then time c to time 2 during restitution. And so if we look at this deformation and then restitution, we're going to apply our impulse form of Newton's second law for each of those phases. And so for T1 to Tc, we get the mass of P times the speed of P at time c is equal to the mass of P times the speed of P in the normal direction at time 1 minus the impulse from time 1 to time c. And then applying this from time c to time 2, then we get the mass of P, the speed of P in the normal direction at time 2 is equal to the mass of P, the speed of P at time c minus the impulse from Tc to T2. So now we still have our variable that we want to get, which is our speed of P in the normal direction at time 2. But by adding another impulse momentum equation, we've now introduced more unknowns or more variables that we need to solve for. So if we examine our collision closely, then we see that as this particle is colliding with this surface, then the mass is being compressed during deformation, and it's being compressed as far as it will be in the collision. So what we see is that there's a point in which the mass stops moving relative to the surface and just completely stops, and that's time c. And then at that point that it stops, then it changes directions and begins moving in the opposite direction as it bounces off the surface. And so the key here is that at time c, our mass stops. So that means we can come over here, come back to our equations, and then find our speed of particle P at time c, and set this equal to 0. So when the speed at time c is equal to 0, the momentum is equal to 0. And we get to do that in two spots. In our first equation and then our second equation of the momentum of the particle during the first phase, during the deformation phase of the impulse here, and then during the restitution phase of the impulse here. So now we've simplified our expressions quite a bit, but we still have this unknown. So we're still solving for our speed of P at time 2. We're given our speed of P at time 1. And so we still have these unknowns, which are the impulsive forces from time 1 to time c, and then our impulse from time c to time 2. So we use our definition that we've already developed of our coefficient of restitution, which is the coefficient of restitution is the ratio of those impulses, and this is modeling the energy loss in the system, where we have the impulse from time c to t2, and is divided by the impulse of t1 to tc. And so when we substitute these in, we get a negative mp, the speed of p, at time 2, divided by mp, the speed of p, at time 1. We see that our masses cancel, and then that gives us the final expression where the coefficient of restitution is equal to negative the speed of p at time 2 divided by the speed of p at time 1. Alright, so let's make some observations about this expression for the coefficient of restitution. We have a negative sign here, and this negative sign is simply relating this necessary change in direction by that particle, because when it bounces off of the surface, it's going to hit the surface along the line of impact, let's say moving to the right, and then you can see the final phase, we should be moving in the opposite direction when we're considering the normal direction or this line of impact. And so this is simply, once again, equivalent to the separation speed divided by the approach speed. And considering the signs of those, the directions of those. Now the next thing to observe is that this expression, negative Vp at t2 divided by Vp at t1, is really the same thing as if we took our coefficient of restitution between two particles, and then we set Vq, which was the second particle in lesson 21, and we simply set the speed of Vq equal to 0. So that would be a 0 on top at time 2, and then a 0 on the bottom at time 1, and then that gives us the same expression, Vp, negative Vp at t2 divided by Vp at t1. So it kind of begs the question, why not just make that statement last time and say, well, if we've got a surface, we simply just set our velocity of the surface or of particle 2 equal to 0. And the answer is about the assumptions that we make. So why not just do that is because, I mentioned that we're engineers, we make assumptions, and one of the things that we used last time to develop that expression, even though mathematically it's the same, is that total linear momentum of the system was conserved. And in this case, we've got a completely different condition in which we can't say that total linear momentum of the system is conserved, and we have to deal with a single particle and then work out the coefficient of restitution as well as conserving momentum within the tangential direction separately. So mathematically they're the same, but we got there using two different procedures, and that's the important part to point out. So to understand this conceptually, you need to understand, or to understand the dynamics conceptually which underlie these conditions, you need to understand how we got there. An important aspect of modeling the collision between a particle and a surface is now that gives us some tools to be able to measure the coefficient of restitution. And there's a simple experiment that we can use to do that, and that's simply by taking our particle and then dropping it, and then having the material on the particle, material 1, and then material 2 being the fixed surface itself. And then by knowing the speed at time 1, just before it hits the surface, and then by knowing the speed at time 2, right after it hits the surface, we can then estimate what that coefficient of restitution is between the two material properties, and then go use that in other experiments. Now, one of the complications here is that we're violating our assumption, one of our assumptions, and that is that there's no external forces that act on the particle. But to do this, we need to have gravity, and this is the external force that's actually creating the movement, the acceleration, such that we can determine what these speeds are. So we want to analyze this and determine when this experiment is valid and when it isn't, such that we can do this in the laboratory and produce a true coefficient of restitution. So let's define the system that we're looking at. And so here we have T0, which is going to be our initial drop height. And so that means we have a location that we'll call Y0, our initial position above point O, which is inertially fixed. This is our ground, inertially fixed in the inertial reference frame. And then the mass falls, and then just before the impact at time 1, then we have our location at Y1. The impact, the collision occurs, we have deformation, which it flattens out, and then restitution. And then after restitution, we're at the same height, which would be Y2. And then the particle is going to rebound, and then it's going to come to a stop at time 3, and we'll call this height Y3. To apply the results that we just derived, we need to have the speed at time 1 and the speed at time 2, and knowing these heights, Y0 and Y3, we can determine these using a simple energy balance, which we've done multiple times before, which we're saying that the total energy is conserved from time 0 to time 1, and so we would write that as the kinetic energy at time 1 plus the potential energy at time 1 is equal to the kinetic energy at time 0 plus the potential energy at time 0. And so using this energy balance, we'll get our initial condition for time 1, or our speed at time 1, which is the speed Vp at time 1 is equal to, and given our heights is negative 2 y naught g, and then our speed at time 2 will be positive the square root of 2 y sub 3 multiplied times g. And so our signs come from our collision frame, which we haven't defined. And so our collision frame being along the path in which we need to have an E sub n, so positive in the positive y direction, and then our E sub, E sub t is E sub 3, just pointed out of the page, crossed with E sub n. And so we see that E sub t, which we don't use in this problem, is pointing to the left. And so we get our speeds along the line of impact at time 1 of negative square root of 2 y naught g, and then at time 2 being the square root of 2 y sub 3, which is our final height, times g. And so what's different in this situation, we said, is gravity. So when we draw our free body diagram of our particle, and so this is during the collision, then our particle P, we have negative mg in the E2 direction, and then our impulse is Fp time 1 to time 2 in the En direction. And so linear momentum from time 1 to time c is mp Vp times c is equal to mass of P Vp times 1 plus the impulse from time 1 to time c. And then we need to add in our effect of gravity, which is in negative e direction. And so we're only in the line of impact. The integral of the force due to gravity, mg dt. And then from time c to time 2, we get mp, the velocity of p at time 2, is equal to the mass of P Vp at time c plus the impulse from Tc to T2, and then minus the same integral mpg dt. And so this is an integral that we can solve. So we get negative mpg, and we'll say delta t, which is that small time period. And then we'll get a negative mpg delta t for this expression as well. And this is where the time is a very, very small increment. And so when we plug all this in, we get that our coefficient of restitution, being the ratio of these impulses from Tc to T2 divided by the impulse from T1 Fp, T1 to Tc. Then we substitute in, we get mp, speed of p at time 2, then plus mg delta t, and then divided by negative mp, the speed at time 1, minus mpg delta t. And so our final expression is negative Vp at T2, because we're just canceling our masses, plus g times delta t, and then Vp at time 1 plus g multiplied times delta t. Now if we were to simply take these speeds that we have here and substitute them into our equation for coefficient of restitution that we developed earlier, in which we had the condition where there were no external forces, we would say that this is equal to negative speed of p at time 2 divided by the speed of p at time 1, which is our separation speed divided by our approach speed. And so if we were just to substitute that in, then we're ignoring these terms that we have here, where we have our gravity, acceleration due to gravity, multiplied times delta t during the first part of the impulse, or second part of the impulse, and then g multiplied by delta t during the second part of the impulse. So to get from here, which is our true expression, to here, which is the expression that we derived, we would have to ignore the forces due to gravity. And so the only time that we can ignore the forces due to gravity is truly when delta t is very, very small. So we've done this before where we say that delta t is much, much smaller. We write it as 2 less than signs 1. And so when this is the case, then we can approximate, and so let's use our approximate sign instead of our equal sign. We can approximate the coefficient of restitution as the ratio of those speeds that we can measure. And then when we substitute the speeds that we solved for into this expression, we get a negative, and in the numerator it's a square root of 2, the height at 3, multiplied times g, and then divide this by the negative square root of 2, the height at time 0, times g, and so then we get the expression the square root of y3 divided by y0. And so This is an approximation, and that's very important to point out. It's an approximation that depends on, like what we said, is that delta t is very, very, very small. And so as delta t increases, this approximation gets worse and worse and worse. So if you're using a material that deforms and rebounds very slowly, then that's when our approximation is going to fail. And so to use this, you would need to know something about the material or make that assumption. As I mentioned, we're engineers, we make a lot of assumptions, but we need to know that that's the assumption that we're making, is that delta t is very small. All right, that concludes talking about collisions from a particle and a surface, and I'll see you in class.